Okay, let's see. In favor? Yes, okay.
All right, plus negative 1/5 over x minus 1
Okay.
plus 11 over x plus 4. I don't know.
No, didn't.
Like the last three.
Okay, so everyone was good up to here.
Well, I got x minus 3.
Oh, x, no, this should be,
I got 1/3 over x minus
I
1.
got 51.
Negative 1.
okay, so what did you get? Tell me.
51 over 5.
For this one?
No, that one was right.
Oh, negative 1/5?
Yeah.
And you got 51 over 5 here? Anyone else get that?
She's right.
Yes? So 3 people have that?
Yeah, it's 50 now. I apologize.
I'm pretty sure that's what you guys ran. What I got was x minus
Yeah,
3
she's
plus negative 2/5 over x plus 4.
What'd you get?
plus 67
Way off?
by x minus 1.
Sorry, guys. The arithmetic. But yeah, if you could.
Okay, were we all doing this? 10x minus 11
Yes.
over x squared plus 3x minus 4. Were we all doing that?
Yes.
Yes? No? So,
13x over 15.
okay, I think there might be a problem in your long division then. You had this also? You got this, so.
Yeah, I just got a problem in my last minute arithmetic.
Who did not get this as that remainder? Did not get that? Okay.
I got 2x, but I think I did the wrong one.
I'm going to tell you what the correct answer is. Where is this? It's number 47.
Well, there's your problem.
Drum roll.
Hey, my bridge only slightly wobbled, okay? It's still held, sort of. I don't know about 3 months' time. but
This is correct.
That's correct.
This is correct.
So we were right.
This is right. That is right. So yeah, that's the question. If you weren't able to get to this result, you need to go back through and work through it again to see if, because I'm not going to work the whole thing out. I worked one out before this. Just go back in, be meticulous about it.
I was just going too fast at the very end.
All right, so with that, I'm going to give you some to do for homework.
All right.
All right. So for your homework assignment for this one, this comes off of page 908. And maybe look at, increasing in difficulty here. I'm going to give you all the ones that they're like highlighted in the book. Just those. Then maybe 49. That's a decent little mix of problems. And we have about 35 minutes left. And I want to just talk about the last topic of the semester, which comes from chapter 13.
Yeah, because there's supposed to be a
Yeah, and this one, it's in our schedule, chapter 13. We were supposed to cover this. This is actually 12.5. This section is 12.5. It's not in our schedule, but I just decided to do it. Do you see why I like the partial fractions? I mean, there's a lot of algebra in there.
So we're not going to do
So-
13.3 or?
Let me see how far I get with this. All right, I only have 30 minutes, so I don't know how far I'm going to go.
For the homework, does it need a calculator?
Do you need a calculator? No, because you can solve all these systems. Yeah, I don't think the systems are going to get too ugly. They should be all nice. All right, so chapter 13, I'm just going to call it sequences series. Now, when you get to Cal 2, those of you who are going to go on, you're going to see this again, sequences in series. But you'll spend about a third of the semester on this topic. All right, not 30 minutes last day, last week of class type thing. It's going to be a major portion. In fact, a lot of people look at sequences in series as being, 1/3 of the whole course. So you've got, in Cal 2, you've got 3 basic sections, and this is the last part of it in Cal 2. So my only goal here is just to get you acquainted with some of the language and notation and a few of the nice results that we have in terms of sequences and series. So let's start with sequences. A sequence is a list of objects. Now, for us, in this class, they're just going to be numbers, a sequence of numbers.
Random number?
Well, that's a good question. Where's this list of numbers going to come from? So let me give you some examples of sequences, and then maybe we can identify what they are. So some examples. Now, when we write a sequence, we usually put them in a set of braces. So how about 1, 2, 3, 4, 5? That is a sequence, all right? We call this a finite sequence because it only has 5 things in it, right? It's finite. Even if it had 1,000,000 things in it, it would still be finite.
But if it had like the infinity time, then it would.
Yeah, so what if I don't want to stop ever, but I want to keep that pattern? I would write it like this. 1, 2, 3, 4, 5, and then I just write dot, 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 and then close the brace. That's the standard notation that we use in mathematics to mean continue that pattern without stopping. This is what we call an infinite sequence. All right? That's a pretty boring sequence. It's just the counting numbers, right? Positive integers, 1, 2, 3, 4, 5, or the infinite one, 1, 2, 3, 4, 5, forever. Here's some other ones. 2, 4, 6, 8, 10. Those are the even numbers, right? Well, I could do the odds also, right? And if you accidentally put 4 dots, that's okay. All right. Sometimes I get carried away and I'll put 4 or 5. So these are the odds. Right? Those are your odds. What we're interested now at finding is there a way that we can find a formula that would generate the sequence of numbers? So can we find some formula?
I'm sure we could.
So when we say formula, I want you to think of it as a function.
So like.
You plug something in, it spits out 1. You plug something in, it spits out 2. Plug something in, it spits out 3.
So the first one would be y, or it would be.
Like that Gauss function you showed us.
It'd be x.
Oh, that was the one that added up all the first numbers, right?
X is.
I just want to be able to generate the numbers, that's all.
So that would be like just y equals x.
Yeah, this looks a lot like y equals x, doesn't it?
But it has to be greater than 0.
And it can't be fractions,
That's correct.
right? Okay, so you're on the right track. Here's the idea. To create a sequence, and I'm going to look specifically at this one right now, I could define a function, right? Now don't write this down right now. I could write f of x equals x, right? And that should that should create that. If I plug in 1, it spits out 1. If I plug in 2, it spits out 2. If I plug in 3, it spits out 3.
But that particular function, does it include negative numbers, because you could plug in a negative number.
That's right. So that's why I said don't write this down. I'm gonna tweak it a little bit so that you understand you're not allowed to plug in negatives.
Absolute zero then?
No, just hold on. I'm going to use, instead of the variable x, I'm going to use n. And I'm going to say f of n equals n. And it is understood, okay, it is understood that n is an element of that. Now, let me explain what that symbol is. That's a double struct z. Now, we've seen this before, right? Double struct r, all real numbers, right? Z are all the integers. So let me show that to you up here. Z, double struct z, is equal to the set 0, 1, and -1, 2, and -2, both directions forever. So z are all the integers, all right? Understand? Z with the plus on the top right like that means just positive integers. Now see if that makes sense to you. If I define this function f of n to be n, and you're only allowed to plug in positive integers, then you can plug in 0? No, it's not a positive number. So I could plug in 1, it spits out 1. I plug in 2, it spits out 2. 3, 3, 4, 4. Got it? Understand that? Now, with this one, because it's finite, right, I would actually have to stop, wouldn't I?
Yeah.
So I would have to put next to this n is between 0 and 5, and that would stop. So I'm sorry, 1 and 5. I'm only allowed to pick integers that are positive between 1 and 5. So I can plug in 1, 2, 3, 4, and 5, and that's it. Here, it's the same function, isn't it? But I don't have a restriction, do I? If I wanted to write something, I could write n greater than or equal to 1, and that would be okay, right? But if you don't write the restriction, it's understood to be all positive integers. Can you give me the function that would create this one?
Yeah.
2n, good. 2 times n. Because what happens when you plug in 1? It spits out 2, right? When you plug in 2, it spits out 4. When you plug in 3, it spits out 6. Do you all understand? This list is your output, isn't it? This is the output of the function. It's assumed, it is assumed that this is the number that you're getting when you're plugging in 1, you're plugging in 2, you're plugging in 3, you're plugging in 4. Understand this? Okay. How about the odds? How about this one?
But we also, quick question.
Uh-huh.
So if n is always going to be positive, correct?
Yes.
Okay.
Positive and an integer. So it's basically take this stuff out. 1, 2, 3, 4, 5. That's what's going in. So can you tell me what the formula would be to create the odds? 2n minus 1. So what was your thinking through that? Or did you just see it? I don't.
I just saw it, yeah.
So you can't explain that in any way?
I just plugged in n to that, because I was thinking 3 or 1, and it didn't work, so I just.
Okay.
had that constant.
What is 2n by itself? The evens? If you take 1 away from every even number, don't you get an odd? So that's another way you could look at it, right? If I take this 2 and take 1 away, I get 1, and 4 take 1 away, I get 3, and 6 take 1 away, I get 5. Do y'all see that? Go with me? Now, it appears so far that I've kind of addressed this issue of n being in here. That's a domain restriction, isn't it? I'm saying I have a function, but what you're allowed to plug in is restricted.
Yes.
It's restricted. And whenever we're looking at sequences, what we do is really try and make sure that students and other people don't get these mixed up with regular functions. And so we decide that we're no longer even going to use this notation. on the left side, we're going to use this notation. A sub n equals n. So look at, you know how this is f of n? Look at this as being like a of n. Understand? Without the parentheses, this is saying my function is called a, I'm plugging in n's. And when you see it written like this, hopefully there won't be any confusion with the functions we've been studying. And you'll be able to say, yeah, that's a sequence. This over here, same thing. A sub n equals n. This time it's not restricted. This would be a sub n is 2n. And then this one would be a sub n is 2n minus 1. We all right with that? Just notation. I'm going to give you another sequence. I'm going to see if y'all can come up with it. Can you come up with the formula for this? Oh, yeah, dot, dot, dot. Nope, it doesn't go the other way. It's only dot, dot this way. And keep in mind that this one is what we get when we plug in 1, right? This is a sub 1. This is a sub 2. This is a sub 3. This is a sub 4. This is a sub 5, right? So you need to come up with a function that when I plug in 1, it's going to spit out negative 4. When I plug in 2, it's going to spit out negative 2. When I plug in 3, it's 0. A sub n equals negative 4 what?
Plus 2.
No, it could be.
Negative 4 plus 2, that's it?
That's what I'm guessing.
This has to have an n on this side, or else, I mean, that's just the number negative 2.
Negative 4.
Negative 4n?
N minus 1.
But it doesn't go down, that's the thing.
Let's look at each of these. Okay, can I get rid of the negative 4 plus 2? Okay, let's look at this one. If I plug in 1, what do I get? Negative 4. If I plug in 2, what do I get? Negative, plug in 2. Hold on, kids. Hold
Are you
on.
talking about your sequence you have up there, or just that function by itself?
I'm asking you, no, because forget this. We're trying to come up with a formula for this, right?
Right.
And this is a proposed formula.
Well, if you have 2, then it means
Negative 8, right? That doesn't match this, right? You plug in 1, we get negative 4. Plug in 2, we get negative 8. This formula does not work up there. Do you agree?
Yeah.
Okay, so that's not it.
What if it's
N plus 2?
What it?
N?
N plus 2? If you plug in 1, you get 3.
no? Because at 3, that's not right. Because when you plug in 0, it needs to be 0.
Look, when you look at a sequence, try and figure out if you can see a pattern in it. What is the pattern here?
It's going up 2.
It's going up 2 every time, right? And they're all even numbers, right? Aren't those all even numbers? But instead of starting at 2, it starts where?
Negative 4.
So look, could you create this sequence that went that way right there? From here on, could you create that one?
Yeah,
That's just 2n, right?
Yeah.
But you don't want your first number to be 2, you want it to be
negative 4.
negative 4. So how much would you have to take away from this to get back here?
Negative 6.
Minus 6.
So it's 2n minus 6?
2n minus 6. Let's see. If we plug in 1, what do we get?
Negative 4.
Negative 4. Plug in 2, what do we get?
Negative 2.
4 minus 6, negative 2. If we plug in 3, what do we get? 0. Do you see this? I want you to look at it this way, though. Even numbers shifted backwards by 6. You're just taking this and you're moving it back 6 to negative 4. And then it's going to count from there on. Make sense?
Like a parent function.
Yeah, it's almost like we're using that. That's why I always show you evens and odds first, because it's easy to start from those and then build off of them. Okay.
So it's kind of like when you do graphing, it's just shifting it up.
Yeah, exactly. All right, you ready? This is going to get harder.
But aren't we supposed to restrict this or no?
No, it's implied. Look, so this is implied. It's always implied that n is going to start at 1 and go through the positive integers. Always, for sequences. All right?
That's handy.
So z plus is your domain all the time. When you see this, assume z plus is your domain. All right? I'm just trying to figure out where I want to go with you here. Okay, let's see if I can do this.
Can you do
How about 7, 9, 11? I'm going to go kind of baby steps here. Those are odd, good.
Oh, okay.
What created our odds?
2n minus.
2n minus 1 created the odds,
Then we gotta go up 7.
and that started at 1, right?
Yeah.
And we want to move how far to the right?
7?
Not quite, 6, right? So what do you think?
So A of n,
A sub n,
or A, that's what I meant.
that's all right.
A sub n is n, 2n minus,
Okay, that creates the odds, but we want to move it to the right 6, so we want to add 6 to this,
yeah.
which is really going to be 2n plus 5.
Yeah.
Is that going to work?
I think so.
Let n be 1. What do you get? 2 plus 5, 7. Let n be 2. 4 plus 5, you get 9, right? Now look, this is, I'll be honest with you. This is a part of math classes. There's a lot of things like this in Cal 2. It's very difficult to teach something like this. It becomes whether or not the student sees it. And that's really difficult to teach.
Number sense?
It's, yeah, but this is more than number sense. This is just, there's almost an intuition that's involved here. Now, the more familiar you are with numbers, and that makes it easier, but
Number intuition.
just intuition. Yeah, just, all right. So let me give you another one,
So this is gut math.
if you want. All right, I'm gonna go with one of the most important ones out there. This is an example, I'll write underneath it. This is an example of what's called an alternating sequence. Why do you think they call it alternating sequence? It changes from positive to negative, positive to negative, positive to negative, back and forth.
So 1 is n. I mean, n is 1, right?
N is 1, what?
No.
N would be 1.
You're on the right track.
So it's like
Okay.
n minus 1. Okay, so then n
I'll give you that much. It's that.
Whole thing.
Would it be like the square root of n? And it goes back.
It starts with n squared.
N squared. N squared, I don't know. What is n squared going to give you?
No, it's gonna go.
It's going to be 1, then 4, then 9, then... Yeah, that's just going to give you squares.
Something.
That's the technical term.
Negative.
You're getting warmer. Then okay, hold on. Okay, I'm gonna stop you right there. -1, that is correct so far.
I got you. I'm the captain now. Just kidding.
Negative 1.
Oh, it's getting power.
There you go. Okay, now hold on. Is this going to work? You're so close, but you're not quite there. All right, what happens right there? What is -1 to the first power? No, -1 to the first power.
Negative 1. Negative
No.
1. 0, 0.
What's anything to the first power?
1.
What's x to the first power? X. What's -1 to the first power? -1. You don't want that. You want... Okay, so hold on. So if n, let's just walk through this. If n is 1, we get -1. If n is 2, we get -1 squared, we get +1. If n is 3, you'd get back to a negative 1, wouldn't we? If n is 4, we get positive 1. Then back to negative 1. Then back to positive 1. Then back to negative 1, right? This keeps switching. But we want the first one to be positive, right? So if you put plus 1 up here, it will work. Look, if n is 1, what happens? What do you get up here if n is 1? 1 plus 1 is 2. What's negative 1 squared? 1. So you get this one. Now let n be 2. 2 plus 1 is 3. Negative 1 to an odd power is negative 1. So you get this one. Next time you plug in, you get an even. Understand? Yes? Okay.
Yeah. That's what I was trying to figure out. I was like 1, 2, 3, 4, 5, 6, 7. I was like,
All right, this is almost the same thing, except I'm going to start it out with a negative.
so it's just a to the n.
So,
A
I mean,
sub
a
n
sub
Negative
n is negative 1 to the n.
just to the n. That'll work. By the way, the negative 1 has to be in parentheses. Okay. You good? Yeah, I'm going to do more.
Like, I got it, but I think I'll forget it by the end of the day.
Look at that sequence of numbers.
On the bottom, they're odd, on the top, they're even.
it has
So
to be negative.
there is a systematic approach that we can start to take to this when we see a sequence. We can always ask ourselves in the beginning, is it an alternating sequence? So does this switch signs? Negative, positive, negative, positive, negative. Now, how do we create negative, positive, negative, positive? We would have to use something like that in there to create that, right? So what I'm going to do is I'm going to look at this negative sign as being really like a negative 1 out in front. And I know that I can control the sign switching with that negative 1 to the n in front. Then the rest of it is just me trying to figure out how to generate those numbers.
But the bottom one is odd.
Ah, okay. So hold on. I've got this. Do you agree with that? That's going to control my sign switching. Times.
Should there be a plus one though?
I want to start at negative, right? So I'm going to use that one. Okay, now I heard what? I heard odds on the bottom.
Right, the odds are all on the
How do you create the odd numbers
So
starting with
2n
3?
1.
Okay, that starts them at 1.
And
Plus-
then my 3
So 2n plus
minus
2n
plus
plus.
2.
There's 2n plus 1 minus 2.
All right. How do you create the odds? 1, 3, 5, 7, 9, dot, 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 dot. You go 2n minus 1, right? You need to start at 3 instead, so you need to move over by 2 units. Add 2 to this, and you get 2n
Plus 3.
plus 1. I didn't hear it, I'm sorry.
Oh,
2n plus 1. I kept on hearing like 2n minus 2 plus 1 minus 1 plus 2. Do you agree?
Yeah.
What about the numerator?
2n.
Just 2n? Because you're going to start the evens, right? You don't worry about the minuses anymore. You see, we take care of it with this? 2n. That's it. That's the formula that creates that sequence. These are kind of like puzzles in a way. Okay, how about this one? You like the alternating stuff, don't you?
it's kind of easy.
8 minus 13 plus 18 minus 23. I can't count. 28 dot dot dot.
Are you adding stuff? So,
A sub n, gotcha.
Negative 1 to the n part.
Negative 1 to the n plus 1, because I want it to start positive, right? So think about your even numbers, right? For even and odd, didn't you always use 2n for both? You just had to decide if you were going to like add something or subtract.
Yes.
The reason you use 2n is because evens and odds always increase by 2 every time. Do you notice something about these? They always increase by 5, right? If you just ignore the signs, it's just adding 5 to each one, right?
2n plus 1.
2n plus 1 was what gave us evens and odds. The 2n was because it increased by 2 each time.
So it's gonna be this, negative 1 to the n plus 1 plus 5?
No, no. We're going to use 5n to control this.
Oh,
But where would we start if we used this?
Well, I would say 5.
plus 3.
Plus,
Because when it's 1.
think about 5n. What sequence would this generate for you? This would be 5, right? And then 10, and then 15, and then 20, right? And each one of these is that plus 3.
That's what I said.
Yes? I know, I'm just trying to go
Oh,
slow.
okay. I was like-
I'm trying trying to bring everybody along.
I was just making sure I was right. I was like,
Plus 3. That'll do it? Do you see this? Anytime you have, forgetting the signs, anytime you have a common difference between these, 5, 5, 5, right? A common difference. When we looked at evens, what was the common difference? 2. When we had odds, what was the common difference? 2. Anytime you have a sequence of numbers that has a common difference, it's called an arithmetic sequence.
so we kinda
That's
need
its
to
name.
Like algebra.
Hmm?
We need to treat this like algebra. Like a linear equation.
It's kind of like a linear equation, yes. It's just moving up and down. That's all it is. This is a linear equation that grows by 5 every time you step over by 1. Right? This is like your slope, rise over run. It's just where do you start, that moves it up and down. It's a very good way to look at it. Just remember, it's not the whole line, it's just dots on the
Right,
line.
right.
Mhm. Okay. This will be the last one. Those are called arithmetic sequences,
Now,
common differences.
when they do sequences, are you able to introduce variables?
Yes. Yes. Yep. But before you do that, you get the idea of what a series is. And a series is, okay, take that sequence and then start adding them all up. Like take every piece of that sequence and start adding them together.
Kind of like that formula should.
Exactly. Where we were debating, pouring in, and we're not going to get to it. We only have 5 more minutes, and I already promised you the next class is all about the final. So this is it. I mean, the last 5 minutes. So I'm going to take the last 5 minutes to show you a famous sequence.
Are we going to have enough to be able to?
This is something I could throw on the final as a bonus. I give you a sequence, couple of sequences, and you come up with the formulas. Right? These are simple bonus problems. Simple as in simple for me to make. And if you get it, you get it. If you don't, it doesn't hurt you. Okay, how about this one? Have any of you ever seen this sequence before? I'll give you a hint that this is not an arithmetic sequence. Meaning it doesn't have a common difference as you jump up from one to the next.
Something is being an exponent at some point or another.
Maybe. No? Y'all have not seen? No one?
I haven't.
It's not, maybe you have seen it, it's just been a while.
You know what's happening though.
You do know what's happening.
Yes.
What's happening?
1 plus 1 is 2.
Okay, 1 plus 1.
Is 3.
1 plus 1 is 2. 2 plus 1 is
3.
3.
And then add the
2 plus 3 is 5.
Isn't that a triangle? That's a triangle, right?
Not quite.
Didn't you show?
You're thinking Pascal's triangle.
Yeah, that's what I was
Well, I
thinking.
don't
No.
know how to.
Didn't you show a professor this like not long ago?
I showed a professor this?
No, like you were.
Oh,
like,
no. Oh, yes, I did, but it wasn't this one. It was a different one.
I was like-
It was close to this one, yes. This is known as the Fibonacci. I think I misspelled that.
You did. You did say that.
Yeah, no, but this,
Plus minus for the left along division.
I think it's Fibonacci. Fibonacci. It's Italian. This is called the Fibonacci sequence, and it is exactly that pattern. It is the first two are 1, okay? You start with that. What I was showing the other professor was a slight change to the Fibonacci sequence that creates something else that's pretty interesting, but not this one. These are always 1, right? First two are 1. Your next one is the sum of the previous two. So to get this one, I add up those two. To get the next one, I add up the previous two. To get the next one, add up the previous two. 5, right? Next one. Yes? Now this sequence has a formula for it, okay? It is a disaster to look at, and you would never, ever, I promise you, you would never come up with it on your own, all right? If you did, you just go write a paper on that, and we'll give you a degree or something.
Did we get an A if we?
No, it's very difficult to figure this out. In fact, I derived the formula for it the other night, just for fun, and it took a while.
Oh my God.
No. I mean,
Everybody's watching Game of Thrones.
Yes, as we're watching, you know, while we're watching the movie,
Other
he's
one,
like,
yeah.
believe it or not, I had to use partial fraction decomposition to do it, which is what y'all learned how to do. That was part of it. It wasn't original. It wasn't my original ideas. It was something I saw on YouTube of you could get the Fibonacci sequence from this certain thing, and I was like, oh, that looks interesting, so I worked it out. It's very difficult to get. However, there is a way to define it what we call recursively, which means that I can define a sub 1 to be 1, I can define a sub 2 to be 1, and then I can define a sub n to be equal to a sub n minus 1 plus a sub n minus 2 for all n values greater than or equal to 3. What? Okay, so this is what we call a recursive definition. Some sequences are defined this way.
so this is what the definition
That's,
is.
yes, but you know how, it would be nice if I just write down a sub n and give you a formula? That's very ugly. But to write it this way, it's a shorter way of writing a formula, but there's some problems with recursive definitions. First, let's understand what it's saying. It's defining the first two, 1 and 1, right? You plug in 1, you get 1. You plug in 2, you get 1. Got it? Now, this is the formula you will use for any n bigger than 3. So, do you want to know what the fifth Fibonacci number is? Sure. How do I do it? A sub 5 should be equal to what? A sub 5 minus 1 is 4, plus a sub 5 minus 2 is 3. Do you see that that's just saying that the fifth one is the sum of the previous two?
Yeah.
Okay, but do you know what the fourth one is? You do not. What's the fourth one, though, by the definition? It is the third one plus the second one, right? That's what that one is?
So that's 5.
And this one is what? The third one is the second one and the first one. Do you know what the first one and second one are?
1.
Yes, you know what these three are, right? 1, 1, 1. So that's a 3, understand? Now what's this one, though? A sub 2 plus a sub 1. What are those two? 1 and 1? So 1 plus 3 is 5. 1, 2, 3, 4, 5. The fifth one is 5. See, what sucks about the recursive one is if you want to know the 100th Fibonacci number, you have to go back to the 99 and 98. And to get 99, you have to go back to 98 and 97. You have to go all the way back with it. And that's not fun, right? Yeah, it's reversing it. Okay, I'm out of time, but I'm going to show you something. You're free to leave. You won't hurt my feelings. It'll take me 5 minutes. It's called the golden ratio or the golden spiral. It comes from the Fibonacci numbers. This is a square. It has both sides of this square are 1. So I'm going to put a 1 in the middle. It's 1 by 1 square. I'm going to put another square underneath it. What are the sides of that square? Just this one. It's also 1 by 1? Okay, let me show you this drawing. I'm telling you right now, that's a square. What are the dimensions of that one? 2 by 2, right? Because it's 2 here. If that's 1 and that's 1, that's 2. So I'm going to put 2 here to mean it's 2 by 2. I'm going to put another one up here. I'm telling you right now, that's a square. What are its dimensions? 3 by 3, right? Okay, I'm going to do another square over here. What are its dimensions? 3, 4, 5 by 5. I'm going to come down and across. What are the dimensions here? 8, right? 8 by 8. That doesn't look like a square. I'm off a little bit. I'm going to keep wrapping around this way. What's that? 13. Do y'all recognize these numbers? 1, 1, 2, 3, 5, 8, 13. Those are the Fibonacci numbers, right? Do you see them? And then if you start at the first corner of the first box I drew, nope, sorry, this corner, and you go across to the opposite corner with an arc and continue connecting across corners with arcs, like this, you get what is known as the golden spiral. And this is the spiral that occurs in nature when you see snails and you look at their shells from the end. It's not, the spirals are really tight in the middle and they start to spread out. They all follow, and I'm going to put a big asterisk next to this because it's debatable, okay? But most of them appear to follow the golden ratio. That's the spiral, the golden spiral. So it's kind of a weird thing that appears. These Fibonacci sequence appears in nature in different places. It's called the golden spiral, but it's also known as the Fibonacci sequence is used to create what's called the golden ratio. That's what the Greeks used when they were building buildings. They felt like the golden ratio was like the perfect ratio. Like when they build windows, they would use this ratio. Like instead of building a window that was a square, they would build one that was like this ratio. It's complicated. This converges to a ratio called phi. It's a special number, phi. It's called the golden ratio. So
Kind of like E is.
exactly, it's like an irrational number. Okay, all right. We will come back on Thursday and talk about the final, and that's it. Have a good day.
So if you did like a ruler and then like 1 inch, 2 inches, it would come out to like almost a perfect spiral.
Well, it depends on what you mean by perfect